So here I'm going to talk about some more practical aspects of the inversions. Like basically, probably most of you won't have the need to go super deep into that. But then again, most of you will work with the results of the inversion, so you should understand what's happening behind. And inversions are one of these aspects that are very, very tricky. Strictly speaking, we should have an inversion code which is produced by professional statisticians and computer scientists. But we will never have that. And it's currently, I would say it's a big problem, because to develop any sort of code in astrophysics, you need to have a lot of expertise, and most of our expertise is actually in physics and astronomy. But we need to learn how to code and make these things, because it's usually very hard to either get the money or to get people who will sit with you and write the codes. I think we're trying to sort of alleviate this problem with dkist and some inversions, but still, scientists are still very heavily involved in the development of these. And this is a GIF here. Valentin showed you a similar GIF on the first day, which depicts what inversion actually does. So here is a chunk of spectra. This line here, maybe some of you recognize it. It's a sodium D1 line. Here there are two more lines that we are trying to fit. These are photospheric lines of nickel and iron. And here you see, so the observations are obviously red. Down there is, so up there we see Stokes I, down there we see Stokes V. So you see that it's very, very noisy, right? But still there is some signature, right? Even though we have huge amount of noise, still there seems to be something here, okay? And the reason why we obviously see that there is something here is because this is very high resolution spectroscopy. So even though I have a lot of noise, because I'm sampling in a lot of points, I can somehow see the trends, okay? What are the other four panels? The other four panels show you how the atmospheric stratification is changing from iteration to iteration in order to fit these lines here. Okay, and what you can immediately see is that these atmospheric stratifications are not very complicated, right? The temperature looks like some spline or polynomial, same for the line of sight magnetic field, same for the line of sight velocity. And today I'm going to try to convince you why it has to be like that, not like from a physics point of view, but from the inference point of view. And I'm going to talk to you about implementations and how things work, and then I'm going to mention some other things. Before we start, how many of you ever tried to fit somebody writing your own code? So not using NP polyfit or IDL routine or origin or table curve or whatever. 1, 2, 3, 4. Okay, I didn't doubt 6. Okay, well, nice amount. Well, then you know that fitting is can be a very tricky thing, right? And I will touch on some methods, and we have a lot of methods. And basically, it doesn't have to be gradient-based. We use gradient-based minimizations and fittings in solar physics because it's usually most efficient, but it doesn't have to be. There are other methods, and we'll talk briefly about them today. Okay, so let's start talking what the inversion problem generally is. I showed you this picture in my talk yesterday, so let's talk about it in a bit more detail. Here's one column from Bifrost simulation. The independent variable, or the coordinate, is log tau in the continuum. So it's basically a proxy for height, right? We use log tau because we cannot infer things on height scale, right? The reason for that is, it sounds very, very confusing, but the reason for that is actually very simple. If I have my atmosphere at the sun, and we are basically at infinity, if I shift that whole atmosphere by 100 kilometers up or down, nothing will change. The atmosphere, the spectra will look exactly the same. And so although we can sort of maybe infer the relative depths with respect to each other, like for example, I could say in this model atmosphere that I'm looking at, calcium is forming 600 kilometers above the iron. I can't put it on the absolute scale. But we need to know that, and there are methods, physical methods, so we can use, like for example, div B equals 0 or pressure equilibrium or some other things to try and to infer the relative stratification between the pixels in our image. For example, we know the sunspots need to be sort of lower down and so on. But in practice, when we are doing inversions, we can only infer the stratification of quantities on the log tau scale. So I'm plotting you here everything on the log tau. And here we see the stratification of the temperature, total particle density, magnetic field, and line of sight velocity. And you see that these certifications are very complicated. They vary very, very quickly. For example, look at this velocity here. What's it doing? It's first negative, then it's positive, then it drops, then there is this sudden change here. Temperature.
Is this the output of an inversion?
No. This is the input.
Oh, that's
the output will almost never look like this.
Right. Well, it depends on the number of nodes that you put, right? But then you don't trust that.
Then you don't trust that, yes. And so we're now going to go into exactly Valentin's question and try to dissect it. So the thing is the following. You see these things as lines, right? You don't know how points are used to plot this. This could be 100 points, this could be 1,000 points, this could be 1,000,000 points here in this plot, right? It looks like a continuous curve. But in our computers, things are never continuous. We need to discretize it in some way. Maybe I will use 100 points, maybe I will use 100 billion points. The same thing is with the spectra, right? Maybe I plotted this using 100 points, maybe I used, again, 500 billion points. But in practice, it doesn't make any sense. In practice, I will have points here which correspond to my instrument, to my spectral resolution and sampling, right? So keep in mind, resolution and sampling are not the same thing, okay? I can have very poor spectral resolution in my instrument, and still I can sample it with many points. It's not a clever thing to do, but it can happen, right? Same with the spatial resolution. So we usually sample expecting to have diffraction limited, but very often we'll have much poorer performance than diffraction limited. So keep in mind that the resolution and sampling are not the same thing. Back on topic. We know when I give you an array of these quantities, if you sit and read Mihalas enough, you will be able to calculate this spectra here. Okay. But what we want to do in practice is we want to do the opposite. We want to go from these spectra back there, right?